if we looked at this example here, do you see how the numerator is two things being added together, but the denominator is singular? When you have a singular denominator, what can you do to that denominator with its numerator? You have a single denominator. You can split it, right? So what I want to do in this case is rewrite this as the limit as x approaches infinity of 5x over x plus sine of x over x. What happens now to 5x over x? Turns into 5. So you have the limit as x approaches infinity of 5 plus sine of x over x. What did we just say about the limit as x approaches infinity of sine of x over x? Just did it. Previous example. It will always be this.
Has
What?
a horizontal asymptote at y equals 1. 0.
At 0.
Yeah.
So the limit as x approaches infinity of sine over x of x is always 0. What would be the limit as x approaches infinity of the line 5? What's going to happen to the horizontal line of 5? As x gets to infinity, it's going to stay. So we get 5 plus 0 equals, so the limit of this function is 5.
So what do we do for 6 to 6? And that's why it came out so simple for the
Yes. Except for, and that's what we're going to look at. This is x going to infinity. So 66 in the other problem, where x going to 0. So we're going to talk about what's the limit of 0 for x also. And that's what we're going to do right now. So I said I gave you the other pages just so you have blank space, because the example I'm going to do isn't necessarily typed up for you right now. So what I want to do is I want to look at the limit as x approaches 0 of sine x over x right now also. So it's already in your graphing calculators, right? We just did it. So conversely, what's happening as the sine of x over x is getting closer and closer to 0? And we just talked about it. Here's my graph. What's happening as we look at this limit from the left and the right getting closer and closer and closer to 0? It's getting closer and closer and closer to 1. So it is now safe to say that the limit as x approaches 0 of sine of x over x is 1. And the limit as x approaches positive or negative infinity of sine of x over x is 0. We now know these. These are known facts. You don't need to prove them. Anytime you see them, you need to just know this. These are now known facts. Let's switch it up a little bit. What if I asked you to find the limit as x approaches 0 of tan x over x without a graphing calculator? What do you know about tangent? Sines.
Too late.
Just looking at what happens if you look at the x approaching 0 for tan x over x. What can I do to this problem to apply one of these rules? Remember, I'm trying to use what I already know to help me do this. I'm not picking it because I want you to graph it. I want you to use what you know to do it algebraically. So what could you do to tangent? Make this easier, maybe understand it.
Sine over cosine, would that work? You have a 0 over something, so would it equal 0?
So, here's what I want you to see. If you have 1 over x, and you turn tangent to sine over cosine, what is this right here? It's the limit as x approaches 0.
1.
So now, I have the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. Can you see how I can break this into two different pieces? We know this piece right here is 1. What do you know about if you put 0 into cosine? What's the cosine of 0?
1.
Okay. So that would become 1 over 1. So this would become 1. Use what you know to do what you can't. There are one other type of problems where you can use this sign, which is kind of like problem 24. So if you think about problem 24, which I said we were going to talk about how to do that today, it's the limit as x approaches 0, but it's slightly different. It's the sine of 2x over x. I need them to match, right? I need sine of x over x. So what's this missing to make it match in that way? I need this to have a 2. So if I need this to have a 2, how do I algebraically get a 2 in the denominator without breaking laws of algebra? Yeah, I need a 2 up here too, right? And we know that in terms of limits, you can rewrite them. So I could rewrite this as sine of 2x over 2x with that big 2 on top being pulled out in front because it's a constant, and constants get pulled out in front according to our limit laws on that table I gave you. So now, what do you know about x approaching 0 of sine x over x? That 2x over 2x is acting like the x over x. You could replace it with h and h by saying h equals 2x, and you'd have sine of h over h. So you'd still get that. So this becomes a 1, and this is
2, so 2 times 1.
So the limit as x approaches 0 of sine of 2x over x is 2.
What we always want to do, try and just get down to sine of x over x.
You want to have to match algebraically. That's a 2x, you need 2x here. Have to match algebraically. Okay? So that's horizontal asymptotes. So conversely, we need to talk about vertical asymptotes. So vertical asymptotes are the opposite of horizontal. For horizontal, we look at the x values going to infinities. For vertical asymptotes, we look at the x values going to a number, but the answer will be an infinity. So if you think about a graph, here's just some random function. As x is getting really, really close to a from the left, in this case, because we're on the left side of the asymptote. So this would be the limit as x approaches a from the left. For this function, it's going towards positive infinity because the graph is going up. I could draw a second part to this graph and say, maybe the graph also does this and we don't really care. Just kind of moving it all around. But now I could say the limit as x approaches a from the right of f of x is equal to negative infinity. What would the limit as x approached a of f of x be? Well, as x approaches a.
There's no limit. Because first it could be positive, because there's no limit to it.
Well, as x approaches a does not exist because the right and left hand limits aren't equal. Because one goes to positive and one goes to negative. If they both went to positive or they both went to negative, the limit would exist. But because they're in opposite directions, it does not exist. So again, guys, we're kind of talking about vertical asymptotes definition. I don't think you have space to draw this, but this is kind of like what we're looking at. did we learn how to find vertical asymptotes back in the day? What did you do? What did we do to find a vertical asymptote back in the day?
The denominator.
That's the same for today. To find a vertical asymptote, we set the denominator equal to 0. Where graphs have vertical asymptotes, the functions will have an infinite limit. That means that the limit of f of x as x approaches a is an infinity, or more simply that as f of x is increasing or decreasing without bound as x approaches a. So again, that without bound is implying the infinity.
So I guess the same for like square roots, like square root negative, or that's not really big, is it?
No, because a square root is not going to have a vertical asymptote. But like a natural log or an e to the x would, because those graphs actually go down all the way. Where like a square root graph kind of starts here and looks like this. The natural log graphs, they actually look like that. So that would be a vertical asymptote, because that can never go beyond 0.
Mm-hmm.
Where this one just starts at 0. That's the difference. Okay? Example 4, what are the vertical asymptotes of f of x equals 2x over x minus 3? Describe the behavior to the left and right of each vertical asymptote by finding the limits of 3 on the right and the limit of 3 on the left. So, we know that there is a vertical asymptote because if we set the denominator equal to 0, no, because x minus 3 equals 0 and x equals 3. Now, what we want to do is we want to find out what infinity is happening for each of these. So we want to know what's the limit as x approaches 3 from the right of 2x over x minus 3. So what I do is I think in my head, okay, here's my number line. Here's 3. If I'm coming in from the right, what's pretty close to 3 on the right, but isn't 3?
2. Okay,
2, or like 3.1. But those numbers are all going to be, no, not 2, 2's on the left. They didn't even like think about what you said. I said 3.1, going, yeah, okay, no. So 3.1 is pretty close over there. And that's a number I could easily plug into this without a calculator. So if I put 3.1 into my numerator, 2 times 3.1 is, okay, which really at the end of the day all I care about is it's positive, right? If I put 3.1 in down here, 3.1 minus 3 is positive 0.1. A positive divided by a positive is a, so no matter what, the limit of x approaching 3 from the right has got to be going to a positive infinity. And I got that because this is positive. And 6.2 divided by 0.1, I don't really care about it. I just want to know if it was positive or negative. So conversely, we can look at the limit as x approaches 3 from the left. And we think about over here, this would be like 2.9. So pretty close to 3, but still a number I can work with. So 2.9 times 2.9 would be, yeah, positive. And then 2.9 minus 3 would be, so positive divided by negative is a, so this graph is going to negative infinity. So you've now just graphed this function without a calculator around the vertical asymptote, roughly. What do you know about this graph and its horizontal asymptote?
2.
Because the coefficients, x over x, 2 over 1, equals 2. So again, maybe if I drew that line as y equals 2, But again, this would be off a little bit, but we would know this would teeter off at 2, and this graph here would actually come up and be closer to 2. So you can give yourself a rough idea of what this graph would look like, once again, without a graphing calculator. I can see the horizontal asymptote, vertical asymptote. I could ask you what's the limit as x approaches infinity for this function, and you should be able to tell me. Oh, it exists. 2, guys, we just talked about it.
Okay, man.
Horizontal asymptotes are your infinite limits.
Oh,
What's the limit? Again, I like to mix things up. What's the limit as x approaches 3 of 2x over x minus 3? Yeah.
Okay,
Jason, good recovery.
Yeah. I'm just gonna say that. It's like my mom in Jeopardy. That's what they say the answer.
I was thinking it was x as x versus 3.
Okay, the vertical asymptotes for tangent of x. What do we know about the vertical asymptotes of tangent?
Okay.
There's a lot of them, right? We need k. So, the question would be, what do we know about tangent, and what's the rule? How do you find a vertical asymptote? What do you do? What's the rule? What do we say we do to find a vertical? Okay, what's the denominator of tan x?
Oh, wait, tan x.
Thank
No,
you.
cosine.
It's cosine x.
Sorry.
Because tan x. No, you're okay. This is why we do this. I want you to think. I want you to give me the answers, not me to just tell you them. And it's okay to be wrong. Jason. Thanks, I get it.
Jason, don't stress. Don't stress.
See, Steve was just wrong. I'm making fun of him too.
Tranquil's happy, huh?
What?
When is cosine of x equal to 0? No. See, it's okay. It's a pattern. We're yes, at 0. No. No. No.
Wait.
Cosine of x at 0 and pi is 1 and negative 1. And we wonder why I give you trig tests. It's at the top and the bottom, right, guys? Pi halves, 3 pi halves. You know, all those.
At 0, so
Pi.
What did I say?
Yeah, Jason.
Pi.
Seriously.
It's not even Friday. That's not your excuse. So what's the pattern? How's it repeating at pi halves, 3 pi halves? What am I adding to get from 1 pi over 2 to 3 pi over 2?
Okay.
Because the next one would be 5 pi over 2. So it's pi halves plus pi k.
Wouldn't be pi k minus pi half?
But it's pi halves plus pi k.
Can you say pi halves for
Values of k. You'd have to say odd integer values because you'd have to make sure you incorporate the negatives. But yes,
Is this okay?
that would be fine. Pi k minus pi halves.
That's to be true. Does k have to be a positive integer?
No, k is just be any integer.
It could be negative then?
Mm-hmm.
So it's alright?
Yeah, I think so. We just like to make things
That's
obnoxious.
That's what we learned before. What are you talking about?
No, I always add it. Okay? So what does that tell you about the limit as x approaches a? Because we're going to call this right here a. We're going to make that a always. That's why like you changing it, like I was kind of hesitant. Because I'm going based off the pi halves, not the pi k. So what that means is that if I were to graph you tangent, does tangent start at the bottom? Start at the top. Let's go from there. Who knows that one? Okay, and it goes.
There's a little thing. Yeah.
If this right here represents A, the limit as x approaches A from the left versus the limit as x approaches A from the right, for tan x is equal to what?
Infinity of the negative infinity?
Okay, so A from the left is infinity, and A from the right is negative infinity. Does the limit of tangent exist at x equals A? No. Because again, this one would start down here and go up, so opposite sides does not exist. Okay, that's it. And then give you your homework. The pages I already gave you will do tomorrow.
Is it doing this stuff, like with all this stuff?
Yes.